Alrighty, so where we left off at the end of the last video was that we explained or tried to explain how if you take a vector that is perpendicular to a plane or orthogonal to a plane, it's actually perpendicular to every single vector in that plane. How does that help us? So again, our task was to create the equation of a plane, and we said to figure out a plane, or to determine a plane, we need to know two things. We need a point on the plane, that's one, and we need to know the way it's tilted. And again, this is analogous to a line where you need a point and a slope, okay? So maybe we should actually talk about what the equation of a plane looks like first off. And this is gonna be kind of awkward because maybe we don't know exactly why this is the case, but I think part of creating this equation, like when we actually go through the process of creating the equation of a plane, you will actually see why this actually makes sense. But the equation of a plane, so for a line, a linear function, it's, ax plus by equals c, right? Or you could rewrite this as ax plus by plus some constant equals 0. For a plane, it's similar, it's in 3 dimensions. So it's the analogous piece, it's the 3-dimensional analogy of a 2-dimensional line. Okay, so it's ax plus by plus cz plus d equals 0. Okay, bear with me here. This is actually pretty neat. Okay, this piece here is going to help us with actually determining the tilt of the plane. Why is that? Well, notice here. Well, I'll try my best to draw it, right? We'll pretend we're looking at a plane from the side, which basically looks like a line, right? It's hard to define the tilt of a plane in 3-dimensional space because we don't really have a slope, right? I mean, yes, we can visualize a slope, but we have to assume like it tilts some direction in the x, some direction in the y, and some direction in the z. Fractions. This is easy in 2 dimensions on a line because a fraction has only 2 sides, right, as numerator denominator. But we don't have these like 3-dimensional fractions, if you will, or 3-component fractions. But what the tilt does, and again, pretend this is a plane. This is a side view of a plane, a piece of paper. What I can control or notice is this vector, which is perpendicular. Okay, we call this the normal vector. The normal vector of the plane. And again, what's so special about this? This is just some vector that's perpendicular to the plane, but also that means it's perpendicular to every vector in the plane, right? And so if I take, here's a new plane, notice that its normal vector would point in a different direction. It would be slightly more upward, n. And so essentially, to control the tilt of the plane, we really just need to control where the normal vector points. Take a second and just kind of play that back and just repeat it to yourself to convince yourself of that, right? Again, try this in real life. Take a hardcover book or something, or your computer, whatever that is, and say like, okay, maybe I can't describe exactly where it's hard to put into words where it's tilted, right? But if you have a pen sticking straight out of it, where that pen points affects the way that your computer or your screen is tilted. And I realize now I probably should have my screen, my camera on for this, and then that might have helped. Okay. So how does this help? Well, this is how we can figure out. We're going to, the equation of a plane, we're going to combine these ideas here. Okay? So we're going to use the fact that the normal vector of the plane affects its tilt, the way it's tilted. And we're going to also use the fact that the vector is perpendicular to every single vector in the plane. So how do we do that? So we're going to use this particular example, right? Okay, here's the thing. How am I going to get a normal vector of the plane in the first place? We're going to use the cross product, just like that because, well, again, the cross product is perpendicular to the plane that the vectors came out of. Okay, so we're going to use, again, we're going to use this specific example here. Our normal vector is going to be A cross B. Now, there's no reason we couldn't use B cross A, by the way. It actually doesn't matter. But we're going to use A cross B. So again, this normal vector is 3, 9, 1. Okay? Now again, the equation is going to have x, y, and z. So x, y, and z is just some point in the plane. It is some point in the plane or on the plane. Okay? Similar to how xy, like xy, is a point on the line. Okay? So the question is, I need to know, where is the point that I actually know? Well, we have actually a bunch of options here. We know 4 points on there. So just for simplicity's sake, we're going to use, I guess we'll use R. Right? There's no reason we couldn't use P, Q, or S. We just need to know one point that is on the plane. Okay? So I'm going to use that. Negative 1, 1, 2. Sorry, so we're going to grab this down. We're going to slide that a little bit down. So this is the imaginary point that's on the plane. That's going to be where our x, y, z come from. The known point on the plane is R. Negative 1, 1, 2 is a point on the plane. Okay? Why do I need both of these? Well, we're going to use, again, this fact that the normal vector is perpendicular to all the points, all the vectors in the plane. So what I want to do is I'm actually going to create this vector. Okay? The vector that points from one to the other. It doesn't matter which one goes where. We're just going to say that the vector goes from, I'll call this point, what do I want to call this point? I'll call this point M to R. Okay? That vector, whatever you want to call it, you call it vector MR, that's fine, is going to be, again, its components. Well, the x component is, again, the difference in the x, right? Final minus initial. So it'll be negative 1 minus x, 1 minus y, and then 2 minus z. Okay? Remember, we're trying to ensure that no matter what x, y, and z are, if x, y, and z is in the plane, right? Sorry, the point xm, which is x, y, z, is in the plane. That means that this vector n and the vector mr have to be perpendicular. How can I ensure that they are perpendicular? This is where the cross product, sorry, not the cross product, the dot product actually comes in. Because if they are perpendicular or orthogonal, then we know that their dot product is equal to 0. And that's where, by the way, this equals 0 part is going to come into play. Okay, so let's actually do this. So again, vector n is 3, 9, 1 dot, let's see, negative 1 minus x, 1 minus y, 2 minus z, and that needs to equal 0. Let me double check that I actually have my point right. Negative 1, 1, 2. Okay. So let's actually dot this. So remember, multiplying that corresponding component. So 3 times negative 1 minus x plus 9 times 1 minus y. Okay. And then plus 1 times 2 minus z, that needs to equal 0. And so if I distribute, I'm going to distribute this and kind of clean it up just to save some time here. Alrighty, so double check my work, but what I've done is I just distributed each of the pieces, simplified it, and I wanted to make sure all the leading coefficient, the 3x part, I want that to be positive just because it's easier to look at. But we end up getting this, 3x plus 9y plus z minus 8 equals 0, or 3x plus 9y plus z equals 8. And that's the equation of our plane, which I think really, really cool. So if you have just 3 points on the plane, any 3 points in space, 1, 2, 3, we know from geometry that those define a plane. There's only one plane that goes through all 3 of those points, assuming they're not collinear. And yet we can actually figure out their equation, which I think previously would have been something that was really, really hard without just guessing and checking, using vectors, right? We just need to know a vector that is perpendicular to the plane, which we can create by calculating the cross product of, say, these 2 vectors. And then saying, okay, well, that cross product right here, dotted with any other vector, maybe this point right here, like this is XYZ, that dot product has to be 0 because of what we know about the dot product, and that the dot product being 0 assures perpendicularity or orthogonality, if you want to call it that. Alrighty? So I think this is really, really neat. Hopefully you enjoyed it as much as I did, although that is unlikely, I suppose. But hopefully this helps. So I guess in the next video, we'll just run through one quick example of how to just do this on its own. Alrighty? Thanks for watching, and I'll see you later.